This example is one that's going to use the Clausius-Clapeyron equation. Carbon tetrachloride has a vapor pressure of 213 torr at 40 degrees Celsius and 836 torr at 80 degrees Celsius. What is the normal boiling point of carbon tetrachloride? Now this is a two-step problem. For one, it requires us to know that the normal boiling point is defined as the boiling temperature at 760 torr. So to start this problem, you do it like any other problem that you might do in chemistry. You start by defining your variables. I have done this here, where I've defined P1 as 213 torr, and then T1 is the temperature at which that 213 was achieved. So they are grouped together. That's important because when you put them into your equation, you have to make sure that your T1, whatever goes on top, is the entity that is being subtracted in this side of the equation. If you put your T1 pressure here and you put your T1 here, you will always get this wrong. Okay, mathematically, you have to pay attention to where you're placing your variables. Then the other variable defined, I'm going to define as P2, where 836 torr goes with 80 degrees Celsius. And then I'm going to define a third variable because we were asked not for either of those two, but instead for what is my T3, my temperature, which is at a pressure, I'm going to call that P3 equal to 760 torr. So if I'm going to use this equation then, how am I going to do this? Because there's no way I can stick all three of these into the same equation. There is, requires a whole lot of rearranging. Probably easier if instead you solve for the one variable you don't have and then use this same equation again, but sub in that new variable that you just found. Meaning, the only variable in here we don't know, we know R, we know the different pressures, we know the temperature, it's our enthalpy of vaporization. And so because we don't know that yet, we could look it up in a table, but that's not really what this problem is getting you to do. So you can solve for it by using your T1, your T2, you solve for it, and now you can do it again using, doesn't matter which one or two, but say you use 1 and T3. And if you do that, now you can solve for the final T3 that you're looking for. So let's do that. Let's break it into two steps, where the first step is solving for our enthalpy of vaporization. Why vaporization? Well, we're vaporizing it. We're looking at vapor pressure, so that is the gaseous state, temperatures at which the substance has already boiled. So let's do that. Let's plug in your P1, your T1, your P2, and your T2 into this equation. Go ahead and stop the video, plug them in, turn the video back on, and see if your numbers match the ones I have put on here. Remember, look up R, remind yourself of what R is and what the units are. Here's a little hint before you do that. Are you going to need to change your units for your pressure? Because typically you're like, I need to change it all and put it in an atmosphere. At least that's what you might have remembered if you were doing the gas laws ways back in Gen Chem 1. But since they're going to actually cancel out, you don't need to do that in this case. All right, go do it. Welcome back. So you should have gotten this. What's the other big difference you might have not caught on to? I warned you about the pressures, but I didn't warn you about this. Why? It needs to be converted to Kelvin. Why? The R has mole times Kelvin, so that's what's going to cancel here with this K here. This K is going to be on the bottom. Since this is on the bottom of a bottom, it's going to be on top, so they're going to cancel, leaving you with joules per mole. So plug all of this into your calculator and then check and see if you got what I got. This is important. Practice with that calculator. I see so many calculator errors at this step. It is your job to figure out how to put in your calculator so you get the right answer. Do that now. So after you've put in your calculator, you should have gotten 31,400.9 joules per mole. Now if you didn't get that, keep trying, you'll get it. If not, come see me. Okay, so now we've got delta H, our vaporization. And so we need to plug this up here into this one. I'm going to go ahead and use my T1 and my P1, and I'm going to use that with this as my P3 in place of my 2s here. Once again, making sure that you're gonna end up with something that makes sense. So I'm gonna end up with Kelvin right here for my T3. So stop the video and try that now. All right, so you should have put your variables in. Your 213 is your P1, your 760 is your P3. This is my T3 then. The T3 needs to be in this location. And then my 3013 is what goes with my 213, which is true here for T1. Put all those variables into your calculator. It's sometimes easier to realize you're solving for a 1 over T3. So the right way to do the math here, Get this number, divide it to the other side, and now you end up with 1 over this minus this. So now how do you get this into t on this side? You add this value to the other side, not divide. And now you have 1 over t3. Now how do you get t3 by itself? You take the inverse. So you bring t3 over here, divide off 1 divided by whatever you had already on this side. Okay, algebra is fun. Make sure you got this. Okay, and you should end up with the end with T3 is 350 Kelvin, which is 77 degrees Celsius. And this is a really big problem, about as hard as I can make it for a Clausius-Clapeyron equation.